In the last video, we had extended the definitions of position, displacement, velocity, and deceleration to 2 dimensions and had explored the consequences of that using graphical techniques for vectors. Here now we're going to go and take a look at it using components. And if you remember, when we did things with components, the rules for addition and multiplication were that you did things slot-wise, so you would add x components together, add y components together, and so forth. And so you can follow all the same things we did to get the gang of 4 in 1 dimension again, but it'll be that you'll get 2 relationships. One of them will be for the x components of everything, and one of them will be for the y components of everything. I like to think of this as the land of x and the land of y. There's a big wall between the land of x and the land of y, and nothing can be traded back and forth between these. So you can't solve for v sub x and then somehow try to insert that into something over here in the land of y. You couldn't say solve for y and try to somehow insert that into anything over in the land of x. You can't communicate any information between the land of x and the land of y, except it's pretty much almost always the case that whenever there is a large wall erected between nations, there's a tunnel underneath the wall somewhere. And the one piece of information that can go through the tunnel is the time. And this will turn out to be super useful. When we do kinematics relations in 2 dimensions, basically what you can do is you can treat it as 2 separate 1-dimensional problems. One of them involving purely the x components, and you go over to the land of x and you solve the kinematics, that part of the kinematics problem in the land of x. And then for the y component, you go to the land of y and you solve that particular kinematic problem in the land of y. The thing is that the one new wrinkle here is that when I gave you the procedure for how to determine which of the 4 equations in your gang of 4 you would want to use, I had asked you to identify the missing variable. The new wrinkle here is that sometimes you'll find that there are 2 pieces of information that are missing. If that's the case, it'll always turn out that one of the pieces of information that's missing will be the time. So what you can do is you can go to the other land, solve for the time, send the time through the little tunnel under the wall to the land that you care about. Most often you're going to be using the y equation to solve for the time, and you'll plug that over into the land of x. But it isn't totally impossible to have a situation where you use the x equations to solve for the time, and you stuff the time through the tunnel over to the land of y. So it can go in either direction. It just depends on the problem at hand. So I think this is probably one of those things that's best done by example here. And so I'm going to do a few examples to help you get a bit of a feel for this. So in the first example that I'm thinking of, we can just imagine that you're on a cliff. There you are. And you're really happy because you're about to throw a ball. And you throw the ball at 5 meters per second purely in the x direction. So since you're throwing it purely in the x direction, that tells us that the initial y component velocity will be 0 meters per second. We're going to let the ball fly for 2 seconds. And what I would like to know is what is the speed at the end of that time. So notice I asked for the speed, but it'll turn out here that what I'll have to do is I'll have to actually solve for the velocity. I'll have to solve for the x and the y components separately because I always have to do that. I can only solve for the x piece in the land of x. I can only solve for the y piece in the land of y. And then at the end, I'll use the Pythagorean theorem to put them together. So when you're doing a problem like this, first thing that you'll always want to do is pick a coordinate system. I'm going to do this one twice just to give you some options. So in my first go around at doing this, I'm going to say make the usual choice of coordinates that we make, that plus x is to the right and plus y is up. With that choice of coordinates now we can write what a sub y is. Since this is going to be under free fall, the magnitude of the acceleration will be 9.8 meters per second squared. And since it's going down, that will be in the negative y direction. So we'll pick up a minus sign there. Okay. So now, when I solve a problem like this, I like to demarcate off separately the land of x and the land of y. And if need be, we'll trade some information between them later, but let's just go for it now. So here in the land of x, what I want to find is what is the final x component of the velocity. So this end, I should ask myself, what variable am I neither asked for nor given? I am given that a sub x is equal to 0 meters per second. We live on the Earth after all. So with that, I'm being asked for v sub x, so that is not missing. With a moment's reflection, I realized that I'm not asking at all about the x coordinate of the ball. So that means I can use the missing x relation. So that's going to say that Vx equals V naught x plus 2 a sub x times the time. Now, normally I'm not a fan of putting the numbers in right away. The one place where I will make an exception to that is if the number is 0. Here, a sub x is 0. So that tells me that the final x component of my velocity is the same as the initial, which is 5 meters per second. Okay, so we've taken the land of x as far as we can. Now let's go over and visit the land of y. It's going to be the same procedure. V sub y is what we need to find here. And again, it'll be the same deal. I'm given a sub y, I'm given t, I'm asked for v sub y, so y is what is neither asked for nor given. So this one's going to say v sub y equals v initial y plus, oh my gosh, plus a sub x delta t there, plus a sub y t. Okay, here v naught y is 0, so we can go ahead and put that in right away. We get that ay is minus 9.8 meters per second squared times 2 seconds will give me 19.6. Let's check our units here. Yep, meters per second. So the units check. All right, so now we're almost done. What I've found, whoops, my bad, minus sign. So what we found is that the velocity looks something like this, where Vx is 5 meters per second and Vy is minus 19.6 meters per second. So by the Pythagorean theorem, since v is the hypotenuse here, my speed v will be equal to the square root of vx squared plus vy squared. So this will be the square root of 5 meters per second quantity squared plus negative 19.6 meters per second quantity squared. All right. So remember, when you square the number, you square the unit as well. So this will be, when I square this will be 5 squared, 25, meters squared per second squared. Same kind of deal here. I'm going to get meters squared per second squared. Good. When I add these, they have compatible units. So when I put the numbers together, this will have meters squared per second squared. When I take the square root of that, the square root of meters squared per second squared is indeed meters per second. And when you grind the number through on your calculator, you will get 20.2 meters per second. Alrighty. Now, I promised you that I would redo this problem with a different choice of coordinate system. And this is purely a matter of personal taste. You're not a good or a bad person if you like or don't like this. But what I find sometimes is that it's, for me personally, I often find it helpful to make, in these kind of problems, to make down positive. So how can that possibly help me here? Well, if I make down positive, so let me just move my plus y down there. If I make down positive, it has the advantage of making the acceleration positive. So that information was all the same. Let me copy through here. There we go. Now the only difference is that my a sub y, instead of being negative, is positive. That's literally it. All right, so for solving the problem, you would be doing it exactly the same way. You would demarcate out the land of x and the land of y. And again, we realize that here I need to know what Vx is, here I need to know what Vy is. Again, we would be using the missing x equation, so we'll have that Vx equals V initial x plus AXT. AX is 0, so this is still 5 meters per second. Here we'll be using the missing y, just like before. It's the same logic. So that would be Vy equals V naught y plus AYT. V naught y is still 0. But now this would be plus 9.8 meters per second squared times my 2 seconds to give me my 19.6 meters per second. And here it's positive. And positive just means that it's going in the direction of positiveness, and which in this case is down. So we would still realize that it was the same triangle we had. The only difference is that instead of Vy being negative, now it's positive. And so when we find the speed, we'd be doing the same thing as before. It's the square root of Vx squared plus Vy squared. So this would be the square root of 5 meters per second squared plus 19.6 meters per second squared is still 20.2 meters per second. So whichever way floats your boat. Now in this problem here, it's pretty low. You know, it's hardly one thing or the other to make the choice, but sometimes you might find it more convenient to make down positive if you realize a lot of things are going down. you could choose to make down positive and make the math a little easier. But on the other hand, if you prefer to just always keep up positive, there's absolutely nothing wrong with that. I'm just presenting this as an alternative. All right. In the second example that I want to think about here is I'm thinking about in the world of archery, there is a discipline called flight shooting. So there you are, shooting your bow. That's an awfully long bill on your cap. Let's give you a more reasonable bill on your cap. There you go. So there you are, shooting your bow. And in flight shooting, what you do is you shoot for distance. So we're going to go ahead and figure out how far did the arrow go. Now, some typical values for a typical bow. Okay, my bow. Hey, the channel is Physics FITA. Did you ever wonder what the heck the FITA was about? That's the old acronym that stands for Fédération Internationale de Tir à l'Arc, which is the International Archery Federation, which is what it used to call itself before it renamed itself World Archery a few years back. Anyway, moving on. I'll let you pretend that the initial height of the arrow is 0, even though that isn't strictly right. It's going to be about a little over a meter because it's going to be up at about the height of your shoulders. But just to make the problem a little easier, let's make it 0. All right. So then over here where we land, the height is 0. We can choose a coordinate system. Let's just go with the standard up, down, right, left, like before. Oops, there we go. Derp. I did not mean to do that. All right, let's try that again. And this time we'll put it right where I mean to have it. There we go. So this will make this the plus y, that the plus x. Now, let's say, for sake of argument, that the angle that the arrow was fired at was 30 degrees. And we'll say that the arrow was initially going at 60 meters per second. Now notice I did not say v0 x and v0 y, just v0. This is the initial speed of the arrow. All right. Now for this one, we know the acceleration. Since it shows, we know that ax is 0. And ay, since it shows up to be positive, will be negative 9.8 meters per second squared. Neglecting air resistance, which, let me tell you, in the world of archery, neglecting air resistance in the real world is a very bad idea. So this isn't going to be a winning shot by any means, but the distance that we get out of this will be pretty typical. So, all right, same deal as before. Let's just start going for the jugular here. We'll go ahead and demarcate off our land of x and land of y, but let's just start with the land of x and see if we can figure out a relation that we can use. First off, we realize before we even get to this that we're going to have to figure out what v0 x is. We kind of have it already. We drew in, there's my v0. So this piece right here would be v naught x. So that's my angle theta. This will be equal to, so v naught x will be equal to v naught times the cosine of our launch angle. By the same token, we can work out that v naught y, because we will, spoiler alert, need to go to the land of y. V naught y will be v naught sine theta. Alrighty. So with that, let's go start identifying the missing variables. So what's neither asked for nor given? Well, it seems like going for missing t might be the way to go, right? So let's try that. The problem with using missing t is if you start saying v squared, vx squared equals v naught x squared plus 2a sub x, x minus x naught, and we're free to make x naught equal to 0 here. This all seems good, right? You can just immediately take this and rearrange it to get that x is vx squared minus v naught x squared over 2ax until you put in that 0. And then you go crap. That's my attempt to write a Grolix there. So then you find yourself going crap, you're dividing by 0. That doesn't work out. You could also, and so then you're stuck because in order to solve this, any of the other relations are going to need the time of flight. So to that end, we're going to have to go and take a visit over to the land of y to solve for the time of flight. Now here, we do know the initial and final position. We know the acceleration. We know the initial velocity. What's missing is v sub y. So, okay, we can start writing that down. That's going to be y equals y naught plus v naught y t plus 1/2 ay t squared. All right, let's put in zeros where we can. Okay, that's 0. That's 0. That's awesome. So when we solve for the time, what we're left with is 0 equals v naught y t plus 1/2 ay t squared. Okie dokie. So this is a quadratic. And certainly you could go and solve this using the quadratic formula, but in this case it'll be easier to just factor it. So let's factor t times v naught y plus 1/2 ay t. And so you remember that we'll have two roots. One root if this term is equal to 0, the other root if that term is equal to 0. So if we look at our two roots, whoops, my bad. If we take a look at our two roots, looking at the red term, okay, that one, we can just write that one down immediately. T equals 0. And we're going to discard that root. Ask yourself, why are we discarding that root? Pause and I'll get back with you. Okay, the reason we're discarding that root is because at t equals 0 is when you launched it, which is a height of 0. What the roots are giving you is just the times from the height of 0, and the t equals 0 root tells us that it was at height of 0 when we released the arrow. So what we need to solve for is the case when the sort of pink color terms is equal to 0. So this is where v naught y plus 1/2 ayt equals 0. So 1/2 ayt equals negative v naught y, t equals minus 2 v naught y over ay. Now, you should be pausing here for a second saying, wait a minute, I see a minus sign in front. It sure as heck looks like that you're telling me that the arrow hit the ground before it was fired, which would make absolutely no physical sense. So clearly you must have made some sort of a mistake. And I would assure you that I did not. And I would ask you to think about why I did not make a mistake here. All right. So the deal here is, remember, your ay is negative. So since ay is negative, negative times a negative sign is positive. So the time when we put the numbers in, the time we get will be positive, even though we have this explicit minus sign. So we'll have to carry that explicit minus sign as we go ahead and send that information back over to the land of x. All right, now take 2. We want to figure out, so the other variable that was missing, so now we can try this one, was the missing, we were missing, my bad here, Vx. In fact, you can see that we would have had a problem here even if we knew Ax, because Vx was something that we weren't provided. You can very quickly convince yourself it's equal to v naught x, so then this is 0 over 0, which is even uglier. But anyway, so now we can go ahead and use the missing Vx. So this will say x equals x naught plus v naught xt plus 1/2 a sub x t squared. A sub x is 0, so we're allowed to put that in right away. X naught is 0, so we're allowed to put that in right away. So our value for t that snuck in through the tunnel from the land of y was negative 2 v naught y over ay. So we're going to put that in there to get that my final position is negative 2 v naught x v naught y over a sub y. All right. We can clean this up a little more. We can remember that v naught x is v naught cosine theta. So this will be minus 2 v naught x cos theta. And then v naught y was v naught sine theta. This will be over a sub y. Okay. So this finally gives me that x is equal to negative 2 v naught squared sine theta cosine theta over a sub y. And you could clean this up a little more if you're really clever with your half angle and double angle relations from trig, but you know what? Life's too short. Let's just plug and go. So this is minus 2. My v naught we said was 60 meters per second. We'll add the sine of 30 degrees, the cosine of 30 degrees, and we'll divide by negative 9.8 meters per second squared. So those minus signs will indeed cancel each other out. I'll be left with a positive sign. Now, before we go and actually crank numbers, let's just take a hot minute and see if the units check before we invest all the effort with the calculator. So we have 60 meters per second squared. I'll have to square that 60. I also have to square the meter and the second. So in the numerator, I will have meters squared over seconds squared. In the denominator, I have meters over seconds squared. All right, well, I can multiply numerator and denominator both by seconds squared, and those would drop. And I can cancel 1 power meters. Hey, check it out. The units are indeed meters. So now that tells me I can go ahead and do the calculator work. When I punch the numbers through on my calculator, I will get that my final position, so how far the arrow flew, is 318 meters. And you should ask yourself, is that a reasonable distance for an arrow to fly? Well, I'm sure as you all know from having watched archery in the last Olympics and have watched the World Championships being streamed on YouTube and all that, you have been, right? The standard distance for the Olympic round is 70 meters. And so that's where people are trying to shoot for accuracy. And at that point, the 10 ring is smaller than a grapefruit, and they're trying to hit that from basically across the, from end zone to end zone almost in an American football field. Or if you're talking a soccer field, somewhere inside one penalty box to inside the other penalty area. So anyway, 318 meters. So if shooting for accuracy is 70 meters, you would think that someone who's just flying and not giving a rip about distance could probably get it a good ways further than 70 meters, and you would be right. For the world record here, let's just say it's a lot longer than this when people are intentionally shooting for distance. So yeah, 318 meters seems totally plausible. Alrighty, and so just to show that the time doesn't always go from y to x, I figured it'd be worth doing one more example. So again, we're back. Before I do that, let me go and do a little rant for a moment. You'll notice that when I got to this relationship, if in some prior existence you have learned a thing called the range equation, you know that I walked to within a gnat's eyelash of the final form of the range equation and then turned away from it. The reason is I am not a big fan at all of the range equation. And I would, if you know it, I'd strongly urge you to try to forget it. The reason is that range equation is only valid if you are shooting across from ground to ground on level ground. Okay, that's fine for things like our flight shooting example, even better for target archery, where the gold on the target is about the same height as the arrow was to begin with. You're talking typically only a few centimeters difference for most archers. So yeah, sure, you could go ahead and do something like that for that. But the thing is just to take our archery example just a little further, what if instead of shooting, shooting for distance or shooting, doing standard target shooting, you're instead doing the discipline of field archery, where you are walking through a course which will have lots of uphill and downhill shots. In that case, you're going to have a change in elevation, but this range equation, if you knew what it was, assumes that there was no change in elevation. So that's why I'm not a fan of special purpose equations. If you start from things that you know are true, then you will end up with something. Then you'll end up with something that you know is true. If you just were to willy-nilly grab this range equation, if you happen to know it from a previous lifetime, there you could get yourself into some trouble because it might not apply to the situation that you care about.